Hey scholars, I hope you all are doing great today. We are about to start a new unit on radical functions. So the first lesson of this unit is going to be over radical expressions. We'll review some things that you've already seen before, that you're already familiar with, and we'll take it a step further as we practice simplifying radical expressions that are of a higher order, or we might say to the nth degree. I'll make more sense of that as we go through this lesson. Let's get going. So let's start off by just reviewing some things that you've already learned. Squaring a number and taking the square root of a number are inverse operations. So some examples, you got 2 squared equals 4, and the square root of 4 equals 2. Or if we do this, if we take the square root of 2 squared, let me do this, the square root of 2 squared, well, that equals 2, right? The exponent of 2 and the radical, that square root, they're going to undo each other, okay? Or if we take the square root of 2 and we square that, like I have right here, that will equal 2, okay? It's like that exponent of 2 sets that 2 free from its cage when we square it, okay? So square root and the exponent of 2 are inverse operations. So let's say we have 2 cubed, and I want to get rid of that exponent of 3 and just have 2. I'm going to take what we call the cube root, which I know you've seen before. Well, the cube root of 2 cubed is just going to give us 2. Those are inverse operations. Or if we have the cube root of 2 and I cube that, well, that cube root in that exponent of 3 they'll undo each other, and I'll just be left with 2. They're inverse operations, okay? So make sure you get this written down. The nth root, so that's any root, so it could be the 3rd root, or like cube root, right? Or we could have 4th root, 5th root, 6th root, millionth root, whatever. The nth root of a real number, a, can be written as the radical expression where n is the index of the radical and a is what we call the radicand. So here's a little formula that you could write down. The nth root of a, where n is the index and a is the radicand. Okay. So now let's figure out what is the index, radicand, and value of the cube root of 8. All right. So well, let's think for a second. The index is 3 because that's the value of n right here. That is the index, okay? N is index, okay? The radicand, well, that is a in our little formula there. The radicand is 8. And then the cube root of 8. Well, ask yourself this. What number cubed is 8? Well, it's 2. The value of the cube root of 8 equals 2, okay? What about the 4th root of 1? Well, the index is, let's say I, the index is 4. The radicand, what's under the radical, right? The radical is 1. And the value of the 4th root of 1 is just 1. Think about it like this. What to the 4th power is 1. Well, it's just 1. 1 to the 4th power is 1, so the 4th root of 1 is 1. Now let's talk about some properties of nth roots. Okay, this is for any numbers a or b that are greater than 1. We have the product property and we have the quotient property. Okay, product property reads the nth root of a product is equal to the product of the nth roots. Let's make sense of that. Here's some examples right here. So here we have the cube root of 16, and I know this might look fuzzy on the video. You should have your slides pulled up. But you can break down the cube root of 16, and I'll just write it right here. Cube root of 16, and we can break that down into the cube root of 8 times the cube root of 2. Since these have the same radical, we could go backwards the other way, and we could say 8 times 2 is 16, Well, and then we'd write our final answer as the cube root of 16. We can also go the other way like we're doing here and break it apart. And here's the deal. We can take the cube root of 8. This is helping us to simplify this, okay? The cube root of 8, like we said earlier, is 2. But we cannot simplify the cube root of 2. So we have to say 2 times the cube root of 2 is how we would simplify the cube root of 16. Let me write that a little differently so that looks more like the index. So 2 times, let's rewrite it right here. 2 times the cube root of 2. There we go, that looks better. All right. Now the quotient property of roots. That reads the nth root of a quotient is equal to the quotient of the nth roots. Okay? So here we have the square root of 25 over 16. Well, when you're given the square root of a fraction here, you're going to apply that radical to both the numerator and the denominator. So square root of 25 over 16 equals the square root of 25 over the square root of 16. And the square root of 25 is 5, the square root of 16 is 4. Okay? And here we have basically some formulas that you can use for that. So those are a couple examples of those product and quotient properties. Here are a couple more that you'll see on your slides. Okay, here are a couple examples for you. Maybe a little more complicated examples, but it'll probably be helpful, I believe, to look over those. Now, let's practice working some problems here. All right, so we want to simplify each of these expressions. And we're going to apply those properties that we just learned. Okay, so follow along with me. We've got the fourth root, so the index is 4, right? We've got the fourth root of 80 x to the fifth y cubed. So here's how I'm going to go about this. I am going to first look at the number 80. Okay? Let's look at the number 80. And I want to break it down into its prime factorization. I know that 80 is 8 times 10. This is not the only way you can do this, but here's one way. All right, 80 is 8 times 10. And then I can break down 8 as 4 times 2. And I can break down 4 further into its prime factors as 2 times 2. All right, so there's the prime factorization of 8. Now I need to keep going with 10. 10 is 2 times 5. So now what I'm going to do is, since the index is 4, I'm going to look at these prime numbers. I can rewrite 80 as 2 times 2 times 2 times 2 times 5. Okay, that would give me 80. And I'm going to look to see if I have any groups of 4 here. Any groups of 4. Looking at that index, any groups of 4. All right, so I see 1, 2, 3, 4 2s. Well, here's the deal. I can write 2 on the outside since there were 4 2s, but the 5 is going to be left under the radical. There were not 4 5s, right? So I'm going to write this 2 times 5, the fourth root of 5. Okay, so that's how we break down the fourth root of 80. Now let's look at the fourth root of x to the fifth. And we can break down x to the fifth. We can expand it as x times x times x times x times x. Okay? This is one way of doing this. Now again, I'm looking for groups of 4, right? So I have 4 x's right here, and then 1's going to be left out. So I'm going to take that, I'm going to use this group of 4 x's, and I'm going to put it out here with the 2. Remember there were 4 2's and I just wrote the 2 once? Now there are 4 x's and I'm just going to write the x once. But there's going to be 1 x left out, like I mentioned, right? Well, that x that's left out has to stay under the radical. So we're going to put that right there. All right, now let's look at y cubed. Y cubed is y times y times y. Are there any groups of 4 y's here? No, it's only 3, right? Well, we can't put y out on the outside. Y cubed has to stay under the radical. So, the fourth root of 80x to the fifth, y cubed, simplifies to become 2x times the fourth root of 5x y cubed. That's as simple as we can write that. Here we're going to have a quotient property example because we have x cubed divided by 7 under the radical. And this is a cube root problem, okay? So I can break this down. I can apply the quotient property by saying this is the cube root of x cubed over the cube root of 7. So I can simplify the numerator, okay? The cube root of x cubed, well, we got to be able to recognize those as inverse operations. That's just going to leave us with x. The cube root of x cubed is just x. Now, we still have the cube root of 7 in the denominator. Well, this part might be kind of tricky, so make sure you're paying close attention. What I'm going to do is I want to simplify the radical. I do not want to have a radical left in the denominator. So what I have to do to rationalize, that's what we call this, we call it rationalizing. To rationalize this, I need to multiply by the cube root of 7 to the denominator and the numerator, okay? Now the cube root of 7 divided by the cube root of 7, remember that's just 1. Anything divided by itself is 1. So we're not changing the actual nature of the, we're not changing the actual value of this problem. We're not changing the actual value of this expression, we're just changing its form. Now, this is cube root, right? If it was square root, we would only need to multiply this once. But since it's cube root, this needs to be multiplied by itself 3 times, okay, to undo, okay? If this was fourth root, we would have to multiply it 4 times. So follow along with me, I'll make sense of what I just said there. We're going to have to multiply this by the cube root of 7 times the cube root of 7 one more time to rationalize this. Okay? Now, see we have cube root here. So I have it once, twice, 3 times in the denominator. So what that's going to give me, I'm going to multiply 7 times 7 times 7, and that's going to give me the cube root of 343. All right, so that's the cube root of 343 equals 7. All right, remember, like I said, I want to get rid of the radical in the denominator. So the cube root of 343 equals 7, because 7 cubed is 343. So, see how I've gotten rid of the radical? Okay? Now, let's multiply the numerator. So we've got x, and then we've got the cube root of 7 times the cube root of 7. Well, you know that radical is going to stay the same. And then what's 7 times 7? It's 49. If we are to simplify and rationalize here, the cube root of x cubed over 7, we get x times the cube root of 49 over 7. So I hope that video was helpful for you. I know those examples at the end might have been kind of confusing. And like I mentioned, there's more than one way to solve those, so we can talk about that next class. But come to that class prepared with questions and ready to work. Good work today. Thank you, Collegiate Scholars.